Hi there, today we'll look at Context RCNN, Long-Term Temporal Context for Per-Camera Object Detection by Sarah Beery, Guanhong Wu, Vivek Rathod, Ronnie Votel, and Jonathan Huang. So on a high level, this paper tries to do object detection for cameras where the camera is in the same place for a long time. For example, these wild trap cameras or traffic cameras right here. It proposes to do object detection by incorporating data from the images that the camera has seen in the past to help the detection in the current frame. And it does so via an attention mechanism that it runs over a memory of past data. So we're going to take a look at how this is done and how well it works. And yeah, stick around if you want to know. As always, if you enjoy content like this, then consider sharing it out, telling your friends about it, subscribe if you haven't, and tell me what you think in the comments. So the paper starts off and describes the problem, and the problem is fairly simple. You want to do object detection in images. Object detection is the task of basically, if I give you an image, you should tell me what is on the image and where. So in this case, here, you would have to draw me this bounding box and say, this is a deer. On the bottom, you would have to draw bounding boxes. Maybe they have to be rectangular, maybe not, and say this is a bus. And here is a truck, and here is another truck, and here is a car, and so on. So there can be many objects in an image. There can be one object. There can be objects of different classes, or there can be no objects at all. So this is just object detection, and there have been many papers on this. And specifically, there has been this RCNN, and this is the model that we're going to extend. So the RCNN model, or specifically the faster RCNN model that we're going to build on, is a model that simply detects these bounding boxes in single images. But now we consider the situation where we have a camera that records images for a long, long time. So in these wild trap cameras, they often sit there for months. And it's not that easy to make use of them because in addition to there being a lot of data, they have motion triggers. So that could be there's nothing for a long time, and then there's the animal walks in the trap, and then you have a bunch of images, like one per second for 10 seconds, and then you have nothing again for like a day or 2 days, and then you have 10 images again because another animal walks in or maybe doesn't, and so on, and another. So you have irregular sampling frequencies. You have very, very different distance between the frames. All of this makes it very, very not suited for models like temporal convolutions or things like LSTMs because they don't work super well with data like this. Now, I know there are formulations where LSTMs can do this, but they don't work very well with these super long contexts and irregular sampling frequencies and so on. So the idea is if we have a frame right here, like this one, and we want to detect what's on it, we should be able to pull information from other frames that the same camera has seen, like from this one, or from this one, or from this one right here. And we should be able to do so in a dynamic way. Now, why could that help? If you look at, for example, down here, these images have been taken, they say images were taken on separate days, but you can see this thing right here is in both images. So, or a very similar thing is probably that bus's regular route. So in order to classify whether or not this here is a bus, it might be very helpful to also look at this picture right here and see, it's about at the same location, it looks the same, and also it looks like a bus. So, that kind of gives evidence that this other thing could also be a bus. Then also there are background objects. So sometimes these single frame detectors get confused. It might be labeling this here as a car because just the exact lighting in this picture is just off by the correct amount that it is confused. But considering this picture over here, maybe it recognizes here, no, that's not a car. And it can bring over this evidence to that frame and consider, maybe this is the same thing. So it's not a car. So this is not the same than simply adding training data. We really consider the fact here that these images, they come from the same camera that is in the same location, or maybe that is filming the same thing. So all of this is going to be within the same camera, not just adding IID training data. And with animals as well, like often the same animal has like its regular route, or within these bursts of 10s, the same animal will kind of walk around a bit, and maybe here it's half occluded, but maybe in a different image you see I see the nose. So it helps you make a better prediction. Also, animals are often in kind of crowds, and that helps. If you see that there are other deer around, the probability that this is a deer increases rapidly. So how are we going to do this? What we're going to do is we're going to build an attention mechanism that can do these kinds of look into the past and also a little bit of the future, as we will see, but mainly we'll look into other images from the same camera in a dynamic way, and we'll learn how to address those other images from a memory bank. So the architecture is described right here. Now, as you can see, we are still in the business of doing object detection. So what we'll do is we'll sort of hijack a existing object detector. And the object detector we're going to hijack is going to be this FRCNN, this faster RCNN object detector. That's an object detector for a single frame problem. So that means you have one image and you're supposed to detect what's on it. It has two stages, as you can see. So stage one, if you have an image, and let's say there's some stuff on it, stuff, there's stuff, okay? What stage one is supposed to do is it's supposed to extract regions of interest. This could be, okay, all of these are regions of interest. So it simply says, well, there might be something right here in these regions of interest. And then it describes each of these regions of interest using features. Okay, so it extracts these regions of interest, and each region of interest gets features assigned to it. So, well, I think these are like 7 by 7 by 2048 features. But let's just say, for the sake of describing it, that these are just a vector of features for each region of interest. So each region of interest is going to be associated with one vector of features that this model extracts. Okay, and the next region of interest also has a vector, and the next region of interest also has a vector, and so on. Stage 2 then takes each one of these vectors and assigns a class to it. So this would be deer right here. Okay, so stage 1 proposes regions of interest along with features. Then stage 2 takes each of these regions of interest and classifies them, basically. And I guess there's many in between stages. Like, this is massively simplified. There's non-maximum suppression. There is kind of an alignment stage where you can refine the bounding box and so on. But in essence, these are two stages. And you can see that this system here, it goes in between the two stages. So all of this right here, we shove in between the two stages. So we'll still use the stage 1 and we'll still use the stage 2, but in between, in this thing right here, we'll try to sort of pimp these features such that the stage 2 detector has an easier time classifying. Okay, so we're going to pimp these features by incorporating because these features right now, if you just do it vanilla, these are just from the current frame. And we're going to add to them information from other frames of the same camera. And we're going to do it in two different ways. So the first way, as you can see here, the first way is this short-term memory, and the second way is the long-term memory. Now, the two are slightly different. As you can guess, the short-term memory is going to be only over a short time period around the current frame, and the long-term memory is going to be basically across a very long time horizon into the past. You can see we're trying to classify this blue frame right here, what we call the key frame. So what we'll do is we'll run it through stage 1. Cool. So we have features for each region of interest. And then you can see this goes here, and through these residual connections, this goes into stage 2 over here. So basically, stage 2 still receives the same input. It receives whatever stage 1 outputs for the keyframe. But we're going to add to that twice. So we're going to add two things, as I said. So the short-term memory is added right here. Now, how do we build the short-term memory? We build the short-term memory simply by considering all the frames around the keyframe. And this you can see right here, the current window around the keyframe, which can be like 1 frame around it, or 2 frames, or 3 frames, just a few frames around the current frame. And this can be fairly helpful, as we said. For example, if the deer moves a bit, the car moves a bit, it gets into a slightly different lighting and so on. This can help us very much to classify the current keyframe if we also have features from the surrounding frames. So for each of these surrounding frames, we also run them through the stage 1 detector to also extract regions of interest, and that all of these features go into this short-term memory bank right here. There's different strategies. You don't always have to extract all of the regions of interest. You can also extract just the top one and so on, or you can extract the mean, since these are fairly consistent. The camera's at the same place. There are many ways you can do this, but what you ultimately end up with is a short-term memory bank that kind of is, so you'll have a bank, and you have lots of these feature vectors in here for your regions of interest of the surrounding frames. Now, if this here is your half occluded deer, right? So this is the half occluded deer, and you want to consider information from the surrounding frames. Maybe in the next frame, so maybe this is 3 frames, like 1, 2, 3, and 2 is the key frame. Maybe in the next frame, the deer moves a bit, and you see its nose. And this particular region of interest here is relevant. So how do you now get from this entire memory this feature vector that would be helpful? And the answer is you get it through an attention mechanism. You can see that right here. The way the short-term memory is added is through this attention block. They describe the attention block right here. It is a fairly standard attention mechanism. So I've done a video on attention is all you need. If you don't know what an attention mechanism is, go check it out. But you can see it's very, very standard. So you have these input features, which are the features that come from the keyframe. And you have the context features, which are all the features in your memory bank. You encode the input features into a query using a fully connected layers, and the context features into keys. And then you match the queries with the keys and the softmax in order to get a weighting over the context features. And then you aggregate the values from the context features. So this is a standard attention mechanism. What does it mean? It basically means that each of these vectors right here, they will emit a key that kind of describes what kind of information is contained in that vector. The vector over here will emit a query that describes what sort of information it is looking for in order to describe what's in the region of interest as well as possible. And then you simply match the query with the keys to determine which key fits best to that query, and whichever one fits best, let's say this one here, then you take that vector from the memory bank and incorporate it together with your current information that you already have. So that's how you address things that from other frames using an attention mechanism. Okay, now if this were all, we could train this right now. We could train all of this because all of this is differentiable, right? This stage 1 detector right here is differentiable. It goes here and here, the information. The attention mechanism is differentiable. The stage 2 detector is differentiable, all differentiable. Cool. We can train this end to end. Now, what's the problem? The problem is this long-term memory right here. So in this memory, ideally, we would want to fit, let's say, an entire day, an entire week, or even an entire month of data from one of these cameras. And it's just not feasible that we expand this current window here to an entire month or an entire week for many of those cameras, because even though they have a low frame rate and so on, it's still too much in order to then be all differentiable, all backpropagatable, and so on. So we can't really backprop for this long-term memory. In essence, what we want to do is exactly the same. We want to build up a memory of all of the regions of interest, or maybe selected regions, or all of the best regions of interest, whatever heuristic strategy we have, of the past, whatever this camera has seen, let's say in the last month or in the current week or something like this. We want to build all of this up and then use an attention mechanism, just the same, in order to incorporate it. But we have to come up with these things right here in some other way than a way where we can backprop. So we can't really use this stage 1 detector right here because this is the one we're training, and so we have to backprop through it. Now, an easy proposal is to simply use it anyway, but do like a stop gradient on it, so we don't backprop through it. That is one way, but this the paper decides on a different way. The paper decides that all of the past, basically, right here, and so on, we'll take a pre-trained object detector. So not the one we're training currently, but we'll take a pre-trained one that was pre-trained either on something like COCO, which is an object detection dataset, or you can pre-train it on COCO and then fine-tune it on the task you're interested in a single frame fashion. For whatever way, we'll take a pre-trained object detector or region of interest extractor, and that will give us, for each frame in the past, will give us also the regions of interest along with the features. Okay? And these are the features that we then go and put into the memory bank. Sorry, my tablet just crashed a bit. There we go. Okay, so we'll take a pre-trained extractor right here. That will give us features for regions of interest. We'll put that into the memory bank, and then we will use an attention mechanism to incorporate it. Now, the attention mechanism we can train, but we cannot train the extractor for the features. And this is the difference to the short-term memory, where we can actually train the feature extractor in order to help us with, building the memory. Now the memory is simply built without a goal in mind, basically. And the attention mechanism basically has to learn that it doesn't work with features that are meant for its task. It works with features that have been originally created for a different tasks, and they're not going to change. But as we'll see, this, can be handled. So that's what they do. They incorporate short-term and long-term memory into their stage 2 prediction, and then the stage 2 prediction simply takes in all of those features and classifies the class of the object. And that's the architecture of context RCNN. It's RCNN with long and short-term context. So they describe very different ways of, how they built the memory and so on, how they built the features. I kind of glossed over this right now. There's a lot of consideration in building these things, and you have to look at the paper how they exactly do this. I'm more interested in the high-level architecture and the sort of ideas behind it. So when they do this, they do outperform the current or the single frame baselines by quite a bit. So this SS and this CCT are these wildlife data sets, whereas this CC, I think this is the city cam, these are this street data set. As you can see, they do outperform the single frame baseline by quite a bit. Now, interesting, as you can see right here, as they increase the time horizon of this long-term memory, so they can now choose how much information do they want to put in that long-term memory. As they increase the time horizon for 1 minute, 1 hour, 1 day, and so on, the performance goes up and up and up, which is, a strong indication that these features actually help from the time horizon, because you don't have more parameters. You simply increase the amount of information in the memory bank, and if the performance goes up, you can make a very strong claim that this is actually due to the fact that you have more information in that memory bank. Couldn't really guess any other explanation right here. So they do investigate different memory strategies. They do a lot of ablations right here, where they also say, okay, what if we only have the short-term attention? What if we only have the long-term attention? If we only have self-attention? That means attention only into the current frame, but across regions of interest. That's interesting if you have like a herd of animals and so on. And they all help. But as you can see, the long-term attention tends to help the most in this data set. And the short-term attention helps a lot in this data set if you just compare to the other. Oh no, these are two different metrics, not data sets. Sorry about that. But in essence, it helps the most when you combine the two. And that's pretty cool to see. So they do some qualitative results, which I find very interesting. For example, they can visualize what the attention weights of their models are. So here, you always have a very long time frame, I think an entire month, in this memory bank of the long-term memory. Now, in the top classification, you see the large thing here, the large frame, is the one you actually want to classify. And the other frames are the frames where the top attention score is, so that the attention weights are the highest. So here, in order to classify this, what does the model pay attention to? Or which other frames does the model pay attention to? And you can see right here, they are all spread across the entire month. Here is the timeline. The most attended to pictures are spread across the entire month, and almost or all of them actually have that warthog in here. So this must be like its regular route, and the model recognizes that and pulls in information from all these other images in order to correctly classify it here. On the other hand, on the next example, this gazelle, and tablet crashed, right here, it also puts all the weight on top of images of that same gazelle, but you can see maybe that gazelle was only there for this one particular moment, and all the pictures this camera has of it is, in the very few moments that the gazelle was around. You can see they all come here from the same point in time, or very, very close points in time, and you can see that it puts a lot of weight on wherever the gazelle is. So, that's a pretty strong indication that it actually learns to pull in the correct information, be that from long time horizon or from a short time horizon if necessary. You can also see right here, they visualize the top attention, where the top attention weights go in terms of how long the frames where the attention goes to is away from the frame that they're trying to classify. So these graphics are somewhat kind of weird to interpret. This here always means how much is the total time of the buffer. So the memory buffer here contains always pictures from the total from 1 hour before until 1 hour after the keyframe you want to classify. So this is the frame you want to classify at minute 0, and the memory buffer contains images from 60 minutes before to 60 minutes after. So it's not real time, right? You go back through your footage and you try to classify. So you can also pull out images from the future. You can see there's most attention is on the current frame, which makes sense. You're trying to classify the current frame, and it kind of falls off as you go further and further away. This is across the entire data set, so this is not a specific example, which also makes sense. Probably in most of the time, the relevant information is closer in time rather than farther away. But also you can see that the distribution is pretty spread out. So the model makes use of the entire range of time. And you can see that throughout, even if you have an entire day in the buffer or 2 days, even if you have an entire week before and week after in the buffer, and even if you have an entire month here. And especially if you look at when you have an entire week in the buffer, you can see the periodicity through the days. So that means the model tends to pay attention to images that are from the same time of day compared to the current keyframe. That's fairly good indication that the model has actually learned to address this memory by its content, right? Now, night and day isn't super difficult because you can just go on the brightness and so on, but still, it's pretty cool to see that this is actually happening. They do have some failure cases of the single frame model that their model is able to handle up here, and they make a lot of sense. So here you can see that there's an object that's moving out of frame, and the single frame detector wasn't able to recognize this, probably because it's moving out of frame, whereas this context RCNN is able to detect it, probably because it looked at the frame just before it, where the car was somewhere back here, and it could correctly classify it. Just disregard my drawings. Here, it managed to recognize this animal in the back, whereas this old model, the single frame model, hasn't. Also probably by looking either at frames next to it or by looking at other frames of herds of animals and realizing that usually when there's 2 elephants, there's more. Here you can see that the object highly occluded, so we're talking about the object like at the very edge of the frame. Object poorly lit. This is particularly impressive, and also an example where the animals are often in herds, and if you see one deer, the likelihood that there's other deer is very high in this particular camera, and by aggregating information from different frames, you can see that. Maybe it's always the same patch of deer that comes by. And here, the single frame detector detects this patch here as a vehicle where it shouldn't. And of course, the new model, the context RCNN, is able to recognize that this is present in all of the frames, and in most frames, the single object detector doesn't detect it as a vehicle, and so it can kind of carry over that information. Now, you can already see sort of what the downsides might be. If the single object detector is like very, very, very sure that this is in a single frame, that this is a car, it could carry over that information to the other frames. So even though the single frame detector might have failed in that particular frame. If it fails super hard, it might, shout that to all the other frames, basically dominate the memory, saying like, look, this is a car, I'm like pretty sure, and it will carry over that information to all of the other frames. And they say in one of these high confidence mistakes, it basically detected the same tree as a giraffe over and over again. What I find particularly interesting is they do look at, so here they have this curve of, on the bottom you have confidence threshold, so how confident the model is, and on the y-axis you have the number of false positives. And you can see that in the low confidence regime, the context RCNN has lower false positives than the single frame detector. And the green line here is when you only have positive boxes, so when you only include regions of interest where there is an actual object, which in this case is sort of hurtful. You also want the regions of interest where there is nothing, because that helps you avoid false positives in other frames. That's why the orange line is below the green line. But strangely here, in the high confidence regime, you can see that the single frame model has fewer false positives than the context RCNN. And I like the text that they have to this. In figure 7, we can see that adding empty representations reduces the number of false positives across all confidence thresholds compared to the same model with only positive representations. We investigated the 100 highest confidence false positives from context RCNN and found that in almost all of them, in 97 out of 100, the model had correctly found and classified animals that were missed by human annotators. So basically, these graphs are even underestimating how good that model is, because the model appears to be better than the human annotators of the test set. I find that to be pretty impressive. And here you can see failure modes where they say, for example, when exploring the confident false positives on the snapshot Serengeti dataset, yada yada yada, the 3 out of 100 images, so whatever was not human failure, where context RCNN erroneously detected an animal were all of the same tree, highly confidently predicted to be a giraffe. So this is a failure mode when the model is highly confident it might spill that over to other frames, because we now aggregate the information within the same camera across the frames. To be said, of course, their train test split is such that there's not the same camera in the training data as in the testing data. They have entirely different cameras in the testing data than in the training data, just so there is no information leakage. Yeah, so that's the model right here, how it works. It's pretty cool. It kind of wedges itself in between any single frame object detector that has these two stages, and it's a pretty neat idea to bring in context from the past or even the future of the same camera. Just a quick glance at the appendix. They have lots of different examples right here. In one example, their camera kind of fell over, and they say, well, it still worked. The system was still able to kind of do attention across this failure, this kind of tipping over of the camera. They have more examples right here, which I find pretty impressive, like these super low light things where it correctly detects like the possum. And yeah, I invite you to check out the paper. The code, they say, should be out soon, and I'll see you next time. Bye-bye.